Okay, today we're going to get on to doing statics of particles. Oh, I'm going to try to write a little smaller today because I couldn't fit much on a page, but let me know, especially in the back, if, like, can you see it at that size? Okay. Okay, so um, what's the deal with statics of particles? What's the deal with particles, basically? Um, I'm sure you discussed this in physics, but um, when you're approximating something as a particle, you're assuming that it has no size, um, so that everything happens at a single point. It can have a mass, but no length dimension, um, and therefore there's no rotation that can happen um, because, or I should say, there's no angular acceleration that can happen because if all forces are acting at a single point, you never produce any moments, and so you're not worrying about any rotations. And a lot of, you know, it's not really the object that determines whether you treat it as a particle or as a rigid body. It really is more the application. Um, like for example, like if you're trying to track the motion of a baseball, um, you might want to treat it as a particle if you're going to ignore the effect of spinning on air resistance, right? Because for the most part, you just care about where the center of the baseball ends up. You don't care whether the seams end up, when it hits the bleachers, whether the seams are up or seams are down, right? That's irrelevant to you. But if you're going to do calculations that have to do with the effect of rotation on, um, lift and drag, uh, then you have to treat it as a rigid body. Okay. Um, for some applications, um, treating a car as a particle would be okay, but for some applications it wouldn't, because if you uh, design a car that gets your family where they want to go but gets them there upside down, like a lot of customers are unhappy with that. They always want so much from us. um, okay, so if you treat something as a particle, um, then you're not gonna deal with the moment equation of equilibrium. You're only going to deal with Newton's second law, basically. Um, so the only equation that's relevant if you're treating something as a particle is that the sum of the forces on a chosen object, or a chosen part of an object, is equal to the mass of the body times the acceleration of the body. And in this class, um, that acceleration is going to be equal to 0. So this equation just comes out to the sum of the forces, their vectors, on the body is equal to 0. And so this is the equation that we're going to use over and over again for statics of particles. We're not going to do this for too many classes. We're going to move on to rigid bodies pretty quickly. So what does this equation apply for? This class is called statics, so it applies to things that are still, but occasionally problems are going to come up where you need to remember that this equation applies for objects that are still, and for objects that are moving with a constant velocity. Okay. Because then you don't have acceleration either. And we're going to see one of the things that we're going to do in statics that you haven't done too much up until now is we're going to see that the idea of a body is arbitrary. You know, like you can apply this law for a table, but you can also apply it for a circular quarter-size chunk in the middle of the table. Okay, this law still has to hold. So we're gonna use the flexibility we have of what we isolate. So I'm going to summarize that by saying this holds for any still point, okay, or any part of a thing that we're treating as a particle and it's still, okay. A piece of something is the same to us as the whole object. And this is important. Every application, so this boxed equation here it's still Newton's second law, right? It's just Newton's second law only for some conditions. I'm still going to call this Newton's second law. And every application of Newton's second law, you need a corresponding free body diagram, okay? You should never use this equation without a free body diagram representing it. So I want to give my requirements for a free body diagram. You know, free body diagrams are pretty standardized. I don't think it's going to be too different than what anyone else says you need to do, but I might stress a couple different aspects of it. So a free body diagram. So you're going to choose an object or a piece of an object to isolate. And your free body diagram is just an outline of that isolated body. So that means if your free body is a car, I don't want you to draw the wheels in there. You know, let me show an example. So if your free body is, okay, there's your car, unfortunately, because you're still a student. It's like a Chevy Nova. And it has all these details, right, because it's a real car. Whoops. Headlights. Your free body diagram is just, and I don't care if you put that much, make it that detailed, but it's just the outline, okay? And there's a reason for that. It's because if you draw your free body like this, it's hard to tell, it's not as clear what is exactly the thing you're isolating. You know, it's even worse if you start drawing in the ground and walls around it and stuff. This way it's very clear. Everything on the inside of this outline you're isolating, that's your body, and anything outside is outside of that. And the benefit of that is that when you use Newton's second law, you're going to put in all the external loads, okay? So now you can just go right around the outline and look for things that are touching that body, and there's your external loads, okay? So let me give that more technically or whatever. So the loads that you're going to put on it, sorry, go back up here. So just the outline of the isolated body and the loads, of course. And when we're talking about statics of particles, the loads are just forces. When we talk about rigid body, the loads will be forces and couples. So the loads are the weight of the body and then loads come from anything touching the outline. Okay? So if you're careful about not drawing any details, you just draw that outline. It's just really easy to get all your loads right. You know, you draw a force due to the weight of the object, and then you just go right around the outline saying, you know, oh, here's something, you know, something sitting on the hood, and okay, at the wheel, something's touching there, and something's touching there, and every one of those things produce a force. Okay. If you're doing a 3D problem, it's, you know, you have to think a little harder about going around the three-dimensional outline in your mind, you know, but it's still the same process, gravity and anything touching the outline. So I have a question. This Newton's second law says the sum of all the forces acting on the body is equal to 0. So why aren't we counting any internal loads? Those internal loads are acting on the body. Yep. Well, it's true of rigid bodies actually too. Yep.
All the internal forces cancel each other out.
Exactly. Yep, exactly. By Newton's third law, if you have a force that the wheel is applying to the axle, right? You do have to add that force into the Newton's second law equation. But then you also have a force that the axle is applying to the wheel that's equal and opposite, and that cancels out. The only place that things don't cancel out is at the boundary, because say the ground is applying a force to the wheels, which is part of the isolated body. The wheels are applying an equal and opposite force to the ground, but the ground isn't part of the isolated body. Okay, so in a way we get super lucky with with that, you know. Like Newton's third law says we only have to worry about forces acting from outside on our isolated body. Okay, nice. Otherwise we'd be there all day, you know, because there's a billion internal forces. Okay, so let's look at an example. No, yes. So let's say that we have a mass of 10 kilograms, and it's connected to a support by a cable. It connects to this support at a point B. We'll call this point A. Let me move that. I'll put the coordinate system here. And it's connected to another support at C. So what do we know about these two supports or these two cables? We know that this angle is 30 degrees, and we know that the point B is -2 meters, 1 meter. Okay, and the particle mass is 10 kilograms. And we want to know what are the forces in those cables, or actually more correctly, you could say what are the tensions in those cables, but what I really want to know is what are the forces applied to the mass by the cables. Okay, so if you're talking about tensions, you know you're always going to have just a positive scalar, right? That describes a cable tension. Talking about cables and stuff, that rings a bell from physics, right? But if you're talking about the forces that those cables apply to that mass, you're talking about vectors, right? Anytime you're talking about forces, those are vectors. Okay, so what do we need to do? When I turn the page, this picture is going to be gone. So what do we need to do to represent these forces produced by the cables as force vectors? Well, let me sort of give you a hint here. This is a 2D problem, right? So how many equations are we going to get from Newton's second law? 2 equations, right? So that means that to solve this, we can only have 2 variables, right? And if this cable produces a force vector and this cable produces a force vector, and we're not careful with our variable names, we just call this an unknown vector, 2 variables, call this an unknown vector, 2 more variables, and we'd have 4 variables and 2 equations, and you can't solve that, right? So this is something that came up in the vector review. What are we going to have to do to represent those force vectors? In order to make, if you know the direction of a vector, but you don't know its magnitude, that's the situation we have here. So we have to use the unit vectors, right? So we have to come up with a unit vector representing this and a unit vector representing this. I guess that's getting a little ahead because I have to do the free body diagram first. But that's what we're going to do. Okay, so free body diagram. Well, what do you want to isolate? In this one, it's pretty easy to choose a body to isolate. Right? Yeah, just isolate the mass, right? So there's the mass, and when I said, mentioned what loads go into the free body diagram, or what loads are acting on the body, we know that there's gravity. So that's a force of mg acting down. M is 10, so if we're doing this in SI units, we have 98.1 newtons. And this is the outline of the object. Now we just go around the outline looking for things touching the object, and those each provide a force. So what 2 things are touching that outline? The 2 cables, yeah. So I'll say that there's 1, and by the way, what direction do the forces go that these cables are applying to this object? Away from it, yep. Okay, so I'll call this tension TB because it's going towards that point B. And I'll call this one TC. Okay. So now we have what we need to represent these force vectors as a unit vector times a single unknown scalar, right? Our unknown scalars are the tensions, and we have the directions here. We just need to represent them, you know, come up with numbers for them. So for the one with a magnitude of TB, let's come up with that unit vector. Well, we're going to go B minus A, right? That'll give us a vector in the right direction, but it won't have the right magnitude yet. We'll have to scale it to make it a unit vector. So we have -2, 1. And what are the coordinates of the point A? Yeah, that's the origin. So our vector is -2, 1. And now we need a unit vector. So we have -2 divided by square root of 5 and 1 divided by square root of 5. Eesh. And you get -0.894, positive 0.447. Okay, so then the force vector, now that this has a length of 1, our force vector is just going to be this times our unknown scalar. So TB times 0.894, 0.447. And how about TC? I gave you that information in a little different form. So this time we're just going to use cosine and sine of 30. And that also is the unit vector. Like whenever you do that trigonometry, what you're doing is coming up with a unit vector. You've done that a million times, and possibly you haven't thought of it that way. But that's exactly what you're doing. So you have, let's see, your unit vector is cosine of 30 degrees, sine of 30 degrees. So that's 0.866, 0.5. So the force vector is TC times 0.866, 0.5. And the force vector, you can also, so what's the force vector associated with this load? Express that as a vector in this coordinate system.
0, 9,
Right, 0, -98.1 because it's down. And actually, so you can think of that as a scalar times a unit vector too. The direction is 0, -1, right? And you're multiplying it by the magnitude of that force, okay? So Newton's second law, if we add all these up, says 0, -98.1, plus TB times 0.894, 0.447 plus TC times 0.866, 0.5 is equal to 0, 0. I'm going to give myself a little more room. Okay, so that gives two equations. You have negative 0.894 TB plus 0.866 TC is equal to 0. And I'm going to write it as 0.447 TB plus 0.5 TC is equal to 98.1. Okay. And why did I write it that way? Why did I move the constant over to the other side? Where am I aiming with this? It's because of the way we're going to solve systems of equations in this class. Does anyone here have a calculator that's not a TI of some kind? Okay, that's good. That'll make this easier. So with two variables and two equations like we have here, you could solve that easily by hand. But as the semester goes on, we're going to have systems of 20 equations and 20 variables, and that would take all day to solve by hand. So we're going to solve this as a matrix equation. Your calculator makes it really easy, especially if you have, I think the 89 is the one that just calls it their simultaneous equation solver. But if you don't have an 89, it's easy to do too. You just have to do it a little different way. So this system of equations down here is the equivalent of this. Tell me if you haven't, I guess, seen this before. No, tell me whether you have or haven't. With a yes, I have seen it if you have, and a no, I haven't seen it if you haven't. Okay? Basically, you just need to have done matrix multiplication before to know this form. And I assume you've done that at some point. So you have that matrix times this vector of variables, TB, TC, is equal to the vector 0, 98.1. You know how to multiply vectors to matrices like that? Anybody not had that in a class before? Okay. Well, if you multiply this out, you see that you get exactly those two equations. Okay? And so now how would you solve this? What we want to do is get TB, TC, that vector TB, TC alone. So the way you solve it is invert this matrix. There's actually numerically faster ways to do it, but I think the most straightforward way to think about it is invert that matrix, multiply the inverse to the left of this and the left of this, and you come up with your solutions. You don't have to know what's going on behind the scenes. You just have to use your calculator to do it. But so if you plug this into a simultaneous equation solver, it just spits out that TB is equal to, did I write this right? Yes, That should be right. Okay, so TB is equal to 101.85 newtons, and TC is equal to 105.15 newtons. If you have a calculator like something before the TI-89, there's two ways you can do it. You can do it using the row reduced echelon form. So you enter it in as a, what do they call that? A augmented matrix, where it has the, and then look for RREF, and that'll give you the answers. Or you can enter this matrix, calculate the inverse with your calculator, and then multiply it to this vector. They both give you the same thing. All right, so what I asked for specifically was, I could have asked for the cable tensions, and then we'd be done, right? But what I asked for was the force vectors that the cables apply to the body. So how do we go from the tensions to those force vectors? Yep. That's right. Yep. So actually, like, our answers are in Newton's second law. We just have to now take these variable values that we know and multiply them back in. Okay. So the force applied by that cable going to B to the body is 101.85 times the unit vector, negative 0.894.447. And I didn't multiply that out, but if you multiply that, actually, can someone multiply that out? You can just do it one by one. You don't have to do any vector thing.
Negative 91.1 and 45.45.
Okay. So that's the force vector applied by that cable, and then force applied by cable C is 105.15 times the unit vector 0.866.5. And what do you get there?
91.1.
Oh, really?
No.
Maybe that's, yeah, that is true.
Yeah,
Right.
It has to be the same.
It has to be the same. You're right.
Yeah. And then 52.6.
So I guess if we had that system accelerating, then those two could, if we had it accelerating on a train or whatever, then you'd have MA mixed in, and then those two could be non-equal. But yeah, they have to be equal. Okay, so that's, like, anytime you use Newton's second law, you have to do the free body diagram like that. You have to write out the equation, and we're going to use unit vectors in that way pretty often. Any questions about that? Okay, so now I'm going to give you another rule that we're going to follow throughout this whole course that that you have to follow. Have you guys seen Cool Hand Luke? Like, really? You know what movie that is with Paul Newman? All right, forget it. People like me and your great-great-grandfather used to love that movie. It's not that old. Okay, so I'm going to give you a convention for naming force vector variables, okay? Convention force vector variables. And I'm making the vector clear here because you can't use it on the scalars that, so like for example, in the problem we just did, we were dealing with force vectors, but they depended on these scalars, right? You can't use this convention for those scalar numbers. You could use it for the full vectors, okay? So don't get tricked into using this for scalars that have something to do with force vectors, okay? So it doesn't work for scalars. We're going to name these force variables F for force, subscript AB, and these are vectors, where this A represents the object being acted on, and this B represents the object applying the force. And when you talk about, when you're talking using this convention, say the force on A by B. Okay. It doesn't always have to be A and B. Like if the object being acted on is a car, maybe that would be a C for car, that kind of thing. And we're gonna use this in every problem for the rest of the class. Anytime you have an unknown force vector, use this convention. Okay. Does anyone know what the benefit of this convention is? Have you guys used this before? Okay. I know in D-form we did, right? I don't know that. I think we did. Did we? Maybe not. Maybe we didn't have to use that. But there's a really really nice advantage to writing your force vector variables this way. And it has to do with Newton's third law. Basically, you never have to think about Newton's third law again. It just happens automatically. And it works like this. Anyone have a guess? So the benefit is Newton's third law just ends up being this. FAB. You know what Newton's third law is, right? I just keep saying that. Somebody tell me what it is. Equal and, yeah, right. That's Newton's third law. For every action, there's an equal and opposite reaction. And there's some sort of tricky things to think about with it if you're thinking about it like the philosophers do. But if you're doing it this way, it'll never be tricky again. FAB is equal to negative FBA. Okay? That's the only way we're going to deal with Newton's third law in this whole class, and that's the only way you have to do it from now on. So that says the force on body A by body B is equal and opposite to the force on body B by body A. Okay. Have you ever has anyone ever mentioned that paradox to you before? It's like, okay, you got this horse. What does a horse look like? Has a tail like this. Thank you. And its driver hooks up a cart to it. And you can tell just looking at this horse that he's lazy. And his driver hooks up this cart to him. And he's like, pull this cart into town. And the horse goes, don't you know anything about physics? If I pull on that cart, I apply a force to that cart. That cart applies an equal and opposite force to me, and we don't go anywhere, right? So it's pointless, you know. So I'm not pulling on that cart, and like so that's thinking about Newton's third law in words, and that's when you get into trouble, you know. So anybody want to explain why that doesn't? Obviously, it doesn't make any sense. If you think about it in terms of this notation, then it's sort of clear what the problem is. So draw a free body diagram of the horse. Okay, sort of turned into a dinosaur. So you have these forces. Let's say you have a force on the horse by the cart. You have mg. And where else is anything touching this horse? That's right. So you have a force on the horse by the ground, right? And now draw a free body diagram of the cart. And what forces do you have? You have, I'll call this big mg. And you have the force on the cart by the ground. And then you have the force on the cart by the horse. And now, like if we went and solved all these equations, you could go in and replace this FCH with negative FHC, because that's how this this naming convention works. But okay, so this is equal and opposite to this, right? So the horse was right about that. But the thing is, the horse doesn't move because of the force the cart applies to it. It moves forward because of the force the ground applies to the hooves, right? And his muscles are what makes that happen. The cart, unless the wheels are very poorly lubricated, this force on the cart by the ground is much smaller than the force the hooves, the force the ground applies to the hooves. And so it can't overcome that, and the horse pulls the cart. Okay? So I just think that's sort of a nice example of how you can get into trouble thinking about Newton's third law. If you have a rule, a mathematical way of treating it, you're a lot better off. Okay, notice one thing about this naming convention. In a single free body diagram, if you give all of your force vectors that a name following this convention, every force vector variable has the same first subscript. Because when you do a free body diagram, all these forces are acting on your free body. Okay? So look at this horse. Well, so I didn't do mg as a force vector variable, but if I did do it, it would be the force on the horse by the earth, by gravity. So first subscript is the horse, this would be horse. Go over here, first subscript is cart. Okay? Because that's what a free body diagram is. You're drawing all the loads acting on your isolated free body. Okay. Okay, let's do another example. And this is an example. I'm going to use that convention, but it's a really easy problem, but it's designed to sort of lead into what we're going to do a lot in this class, which is to isolate a body that you don't really think of as its own body. But it doesn't matter. You can take a piece of something as your free body just as well as you can take the whole thing, If you want to isolate, you can isolate a car, or you can isolate its wheel, or a chunk out of its tire, and these laws have to apply in all cases, okay? So let's say we have a tabletop. And in the middle of this tabletop, we have just a little chunk of material, and we want to know what's happening on that. Why would you want to do that? Well, sometimes you would want to be able to do this calculation because you can insert, say, some kind of load measuring device in there, and you need to be able to calculate what's happening in this table based on just a certain point, or sometimes maybe you have a different material in that point, maybe there's a little camera in there or something, and you need to know how to protect it. So there are a lot of cases where you would want to do this. when you go into deform, you want to do this generally for every individual point and figure out what point is in the most danger of breaking, you know. So let's say that we look at a point right here. Okay, just a little chunk out of the middle that weighs 1 gram. And we want to know what total force vector is applied to the chunk by the surroundings. Okay, so a free body diagram. We're going to isolate that chunk. What forces are acting on it?
Gravity.
Yep. And so that's 1 gram is 0.001 kilograms. So this is 0.00981 newtons. Okay, so that's gravity. And then go around the outside and look for places where other objects are touching the outline. So what other force is there? The table, right, the surroundings. And that's the force that we're trying to calculate. So I'll write that as the force on the chunk by the surroundings. Why did I write that as a P? Okay, so now after the free body diagram's done, you can go to Newton's second law, and you get F on the chunk by the surroundings, X and Y, plus 0, negative 0.00981 is equal to 0, 0. So FCS is equal to 0, positive 0.00981. Okay, so this is sort of a simple example. So that's not a very interesting result. It just said the surroundings of the table have to hold that piece up, you know. It just has to counteract gravity. But that's how you solve that. And then what if you wanted to know what force vector does the chunk apply to the surroundings? Well, then you just use Newton's third law. All we're doing is switching the subscripts, right? We want the force on the surroundings by the chunk, and that's negative FCS. So that's 0, negative 0.00981 newtons. Anyone have any questions about any of this? We've talked about the rules for the free body diagram and the naming convention for force vectors, for force vector variables, and how to use that variable for Newton's third law. That all makes some sense. Okay, so when we did that cable problem, we hadn't talked about it yet, so we couldn't use it, but we did that problem without using that naming convention for the variables. How would you use that in the cable problem? Well, the answer is you could use it if you wrote, okay, so let me write this down. So how would you use this FAB notation in the cable example? And the answer is, in your free body diagram, every force every force variable. Like if you know the force, you can just enter the numbers, right? Then we don't care about the notation really. But in the free body diagram, every force variable is either drawn as an arrow and a scalar variable, or a little coordinate system and a vector variable. And this naming convention only applies to that second one, okay? I already said this before, but anything that you draw in your free body diagram as an arrow, like as a direction, and a scalar variable, let's see. So let's say force variables like, you know, group 1 there. Are represented, oh no. In Newton's second law as a scalar times a unit vector. So this is the equivalent of the force AB. Okay, so like in that example, the force on the mass by cable B is equal to TB times that unit vector we found. And once you write it that way, then you can calculate, like, say, the force the mass is applying to the cable with that same Newton's third law approach. Then the force on cable B applied by the mass is negative TB times 0.894.447. Okay. So all I'm trying to say with this is it's very important that you only apply that Newton's third law rule to vectors. And if you want to apply it to something you've represented using a scalar, then you have to put it into its vector form first before you apply Newton's third law. Okay? Does that make sense? Do you know what I'm talking about? Okay. Let's do another example. So say you have a box sliding along the floor at a constant velocity. And you have, the box is 20 kilograms. You have a force horizontal acting this way of 30 newtons. You have a force of 50 newtons acting at 45 degrees, and you have a force of 100 newtons acting at 30 degrees. And the box is sliding to the right with a constant velocity. And the question is, what's the force the box applies to the floor? Okay, so say, I don't know, you work for this construction company and you need to make a floor that can handle these boxes being slid across it. It happens all the time in construction companies. So notice that the question that I asked is kind of the flip of the natural question to ask, right? Because I'm asking for a force that's applied to the floor. So normally maybe your first reaction would be to isolate the floor, right? Because you want to calculate a force that's acting on it. But that's not going to work because there's all these other forces on the floor that we don't know, okay? So what you need to remember is that with Newton's third law, it's always just trivial to flip subscripts, right? So we want the force vector on the floor by the box. It's just as easy to calculate the force on the box by the floor and then use Newton's third law. So in that sense, we're going to isolate the box, calculate the force the floor applies to the box, and then the last step is just to switch the sign and switch the subscripts. Okay, so free body diagram of the box. So we have the 50 Newton force, the 100 Newton force, the 30 Newton force. We have gravity, which is 196.2 newtons. And then there's one more force. Yep. So that's the force vector on the box by the ground. And notice that the free body diagram doesn't change at all depending on what kind of motion you have, okay? It's the same whether it's accelerating or not accelerating or moving constant speed or at rest, okay? Because that's just the left side of, the only thing that shows up in the free body diagram is the left side of Newton's second law, okay? So then when we go to Newton's second law, we have to add the right side of the equation. So we have on the left side, the 100 Newton force is the magnitude times the unit vector that you just get from cosine and sine. The 50 Newton force the 30 Newton force, gravity, and then finally the force on the box by the ground. Oh, I called it two different things, sorry. Up here I called it on the box by the floor. So let's change this to floor. Just click up here on your erase icon and just erase it. Okay, so FBF(x), FBF(y). And now So the free body diagram told us all this, but now we're on our own for the right side of this equation. So what goes on the right side? Well, this is static, so the same thing always goes on the right side. 0, right. It's moving with a constant velocity. So I'm just trying to keep you keep that in the back of your mind that you treat that the same way as something at rest. So 0, 0. Okay, so we have two equations. If you add up all these numbers, you get 21.24 plus f bf x equals 0, and negative 281.56 plus f bf y equals 0. And so the vector f on the box by the floor is equal to negative 21.24, positive 281.56. Which makes sense, you know, the floor has to hold the box up, so that should be a positive y.
Negative 0.5 in the formula, right? Because it's negative y for that number on the top formula.
Negative y, right. Oh, actually, so I did that in my notes. I just didn't write it there. So those numbers are right. Yeah.
I just want to make sure.
Yeah, right. Thanks. And then F on the floor by the ground, that's what I asked for, is just use Newton's third law. So 21 positive 0.24 newtons, negative 281.56 newtons. Okay. Any questions on that? Okay. Well, I posted a bunch of practice problems on this material. So you already have practice problems for the vectors. And now you have a bunch of stuff like this that goes from maybe a little easier to this to a bit harder than this, but it's all sort of in this ballpark. So if you haven't started working on practice problems yet, you should get going, because you're going to get a problem set fairly soon, and you want to sort of drill these fundamentals before you get that problem set. Okay? So thanks. See you on Tuesday.